This is the dreaded blank piece of paper, and while it may not seem like much, it is actually very intimidating to a young engineer. And when you're starting a difficult problem or a new problem and you're given a blank piece of paper to solve it on, it can be really kind of scary, and you say, well, where do I even begin? So in this video, we're going to talk about 5 simple steps that can help you with any sort of engineering problem, any general problem really. And by going through them, you'll see how you can fill up this piece of paper with all the information that you need, write down your calculations, and sort of make it a roadmap to yourself in the future so that you can look back and say, hey, oh, this is exactly how I do it. It's kind of the correct way to solve engineering problems, and while it may seem simple, it takes years to master. And with any luck, we'll be able to make this piece of paper seem not so scary. First thing you want to do, as you might have already guessed, is to read the problem. And you want to be careful about it and make sure that you understand exactly what they're asking. Or if you're not working from a problem in a book and you're actually trying to solve an engineering problem, make sure you're explicit and write it down. It'll help you kind of focus in on what question you're trying to answer. So we're working from a question from a book, and it goes, a large dirigible having a volume of 90,000 meters cubed contains helium under standard atmospheric conditions. Determine the density and total weight of the helium. So we're going to write down, as simple as we can, find density and weight of helium. He is helium. Next thing we want to know, write down is if the problem gave us any information, the givens. And so we can write given the volume being equal to 90,000 meters cubed. The next step is to draw a diagram or a schematic of the problem. You want to keep it simplified to the problem. You don't want to have too many extra things. You want to include key features important to the problem and label, the diagram to make it easier on you and whoever needs to read it. So here's my attempt at a dirigible. Kind of look like that. Little tail. Maybe something like this. Our volume, remember, is going to be 90,000. It's okay to write things a couple times. Just make sure you write them the right numbers. We can label the inside as having helium. And it's simple, it's to the point, it shows what we're trying to find, and it's going to allow us to kind of keep track of what's going on. Next, we're going to want to state our assumptions or approximations, or basically we're going to need more information to solve this problem, and we're going to have to assume some things. So I'll put a little assumptions right here. And so we're assuming, for example, that the pressure or the atmospheric conditions are going to be 101 kilopascals, and let's say the temperature is going to be, that being the pressure is equal to, and the temperature is going to be equal to 15 degrees Celsius. And this is about standard. You want to be able to justify when you come up with an assumption. You don't want to have something off the wall, like you're not going to be flying a dirigible in negative 200 degrees Celsius. So use assumptions that are realistic and be able to back them up if someone asked you about them. Mention any physical laws that we're using. For this problem, we're probably going to be using the ideal gas laws. That also means we're going to need the gas constant, and so that's going to be equal to 2077 for helium. And make sure to include all your units. A unitless number is almost a naked number. If I said our pressure is 101, that means nothing. So our pressure has to be 101 kilopascals to mean something. Our next step is to begin our calculations, and what you want to do is start writing the equations you think you're going to need to use. So for this, we're probably going to need to use the ideal gas law, and that kind of goes that pressure is equal to density, and this is a symbol for density, times our gas constant times temperature. Before we start substituting any of these numbers in, we want to make sure that this is algebraically simplified to our specific problem as best as possible. So we look at this and say, well, we're not really looking for pressure, we're looking for our density. So we could say, okay, then density is equal to the pressure divided by our gas constant and our temperature. Once we have it simplified, then you can go ahead and start substituting our given numbers and our assumed numbers into the equation. So alright, we're going to say density is equal to pressure, which was 101 kilopascals, divided by, let's keep it like this so it's easy for us to read, 2077 joules per gram times K. And remember, this is going to be this has to be converted into newtons per meter squared. So you could say this is actually equal to 101 newtons per meter squared times denominator. We're going to have our temperature, which is going to be 15 degrees Celsius plus 273. To turn it into degrees Kelvin, because our temperature for this equation needs to be calculated in Kelvin.